Hi, this is Module 27 of Engineering Vibrations 1 and Introduction to Single Degree of Freedom Systems. Today's learning outcomes are to define something we call the logarithmic decrement, and then to use that logarithmic decrement to experimentally determine the damping factor of a system. So here's where we left off with a response solution. We see that it has an initial displacement and an initial velocity. The time between two successive peaks is the period of oscillation, and it's bounded by this exponential decay envelope. Okay, there's your exponential decay envelope. The first peak occurs at time t1. The second peak, we'll say, occurs at time t2. And we can put the solution in phase angle form so that it has some amplitude of displacement times e to the minus zeta omega natural t times cosine omega t minus phi, where phi is the phase angle. All right, so the amplitude of displacement that we've seen before is a function of the initial conditions as shown here. So here's that phase angle form. Let's look at the amplitude of those successive maxima at time t1 and time t2. At time t1, the maximum is going to be that amplitude of displacement times minus e to the minus zeta omega natural. And for time, we're going to put in t1 here. And the peak occurs when this argument goes to 0. And so cosine of 0 ends up being 1. And so that's the magnitude of the first maximum, first peak. Same thing for the second peak, except now we substitute in T2. And now let's look at a ratio of those two successive peaks, y1 divided by y2. We can see that we can cancel out that amplitude of displacement, and then we can bring the denominator up in the numerator. When we do that, we see that the sign of the exponential changes from minus to plus here. And then I'm going to substitute in for T2. We see that T2 is equal to T1 plus tau sub d, the period of oscillation. And so I can substitute that into my equation there. And then when I multiply these exponentials, I'm adding the exponents, so I have minus e to the minus zeta omega natural t1 plus the zeta omega natural t1 plus tau d. And if I multiply that all out, I come up with the following. And we can see that the minus zeta omega natural t1 and the plus zeta omega natural t1 cancel out. And I'm left with the ratio of y1 over y2 equal to e to the zeta omega natural tau sub d. And we know that zeta is a constant, omega natural is a constant, and the damp period of oscillation is a constant. And so that value is entirely a constant. So, continuing on from there, I'm going to define the logarithmic decrement as delta. I'm going to give it the symbol delta, and it's going to be defined as the natural log of this y1 over y2. And so the natural log of e to the zeta omega natural tau sub d ends up being zeta omega natural tau sub d. And you'll recall now that the damp period of oscillation is 2 pi over the damp natural frequency, and the omega damped is defined as omega natural times the square root of 1 minus zeta squared. And so if we substitute those in, I've substituted omega d into the denominator here. This is what I end up with for tau sub d. And then I can cancel omega natural, and I end up with delta equaling 2 pi zeta over the square root of 1 minus zeta squared. So we see that delta, the logarithmic decrement, is just a function of the damping factor, zeta. All right, so there is our logarithmic decrement. And since I can measure delta, I can physically take a system and I can look at the decaying exponentials of that system. I can measure it in a number of ways. I get a plot like this, and I can plot it out, and then I can find zeta. So I can take that delta, which is the natural log of the successive peak amplitudes, and I can solve for zeta. Let's do that real quick. If I take and I square this logarithmic decrement, I get delta squared equals 4 pi squared zeta squared over 1 minus zeta squared. Let's multiply the 1 minus zeta squared on both sides, so I get delta squared minus delta squared zeta squared equals 4 pi squared zeta squared. Let's carry those zeta squareds on the same side, so I'm going to get 4 pi squared zeta squared plus delta squared zeta squared equals delta squared. I'll factor out this should not be pi, this should be zeta. And so I'll factor out the zeta squared. And so I get 4 pi squared plus delta squared equals delta squared. So zeta squared equals delta squared over 4 pi squared plus delta squared, or zeta is equal to the square root. Actually, we can take the square root of the numerator, and that just becomes that log decrement divided by the square root of 4 pi squared plus delta squared. So that's the result, and I wrote the result right there. And so, as I said, I have the definition of the logarithmic decrement. It's very hard to measure particularly in vibration systems that are oscillating very quickly, to measure the successive amplitude of the first peak and the second peak. So if you use multiple cycles, you just use delta equals 1 over n times the natural log of that first peak divided by the yn plus 1 peak. So for instance, if you're taking 100 cycles where it decays down, n equals 100, and so you're taking the natural log of that peak amplitude at y1 divided by the amplitude of the 101st peak, which is a lot easier to measure a difference between. And so the bottom line is this can be a free vibrations test. As I mentioned, you can measure the log decrement from a real-world system, and then you can estimate the damping factor, which is a very powerful tool. So there is, for multiple cycles, what we found for the logarithmic decrement. For design purposes, it would be interesting to know, as it says here, how long to decay from y1 to some y sub n. Like, how much decay do I get in, again, 50 cycles or 150 cycles or whatever I want. And so the time for the decay would be the number of cycles you go through times that period of oscillation between each cycle. And so up here, I've solved for n. So I can substitute n in. And you'll also recall that the delta was equal to zeta omega natural tau sub d. So tau sub d is delta over zeta omega natural, and we can substitute that in as well. And then we get the time for the decay to whatever n number of cycles you put in as being this value when I multiply that out. And that's a way of measuring how long it takes to decay from the first cycle to some n number of cycles. Also for multiple cycles, it would be interesting to say, hey, how many cycles does it take for us to get a 20% reduction? We want this real-world system to be reduced by 20%, and how many cycles does it have to go through? Well, again, n is equal to this, 1 over delta times the natural log of y1 over yn plus 1. Since I want to decay 20%, the first peak is going to be y1, and the second peak was going to be 80% of y1, so it decays by 20%. And so if you take the natural log of the y1's canceled, natural log of 1 over 0.8 times 1 over delta, we can then solve for delta, and delta becomes, as you see here, 1 over n times the natural log of y1 over some value a1. In the example, I took 80%, but we can solve for a, and then a is going to give us the percent reduction. We just take 1 minus that a value that we find and multiply it by 100% to see what percentage reduction you get. Delta would be known, n would be known, the y1's cancel, and all you have left is the a to solve for the percent reduction. And so that's a really powerful technique. And so we've defined the logarithmic decrement, and then we use that logarithmic decrement to determine the damping factor for a system. And that's it for today's module.